It is a pleasure to have you here. Welcome, everyone. Welcome to the fall semester for us here in the States. We just started. We're all busy as faculty getting settled, and our students are busy getting settled. It is so great to all have you here. Welcome to a new Co-opting AI session. This is actually our 46th event in the series. We've been going for 5 years. My name is Sloane. I am an assistant professor of data science and media studies at the University of Virginia, where I run Sloane Lab, which is my research group that looks at the intersection very broadly between artificial intelligence and society. I am extremely grateful for the generous support of our partners, that is the UVA Karsh Institute of Democracy and the team at the NYU Institute for Public Knowledge. And as per usual, a big thanks to both teams for making these conversations possible. Now, before I start the show and set the scene a little bit for this big conversation about mathematics, I want to acknowledge that the land where we at UVA learn and work is the homeland and traditional territory of the Monacan Indian Nation. We pay respect to the elders and knowledge keepers, past and present. We also acknowledge and pay respect to the enslaved Africans, enslaved laborers, and free Black laborers who built UVA, as well as their descendants. Today, we acknowledge the land, we acknowledge labor, traditions, and knowledge, and we acknowledge lives. Now, for this Co-opting AI event, we are focusing on the big elephant in the AI room, and that is math. Enshrined in a lot of people's heads as either hated or beloved school subject, math is absolutely everywhere. Mathematical calculations have brought us things like stable bridges and the moon landing. In fact, math was always intimately connected with the production of knowledge and the description of the natural, cosmological, and social world. The arrival of artificial intelligence, however, has made math even more integral to how we organize society. Without math, there is no AI. Many people say that AI is just statistics. Others say it's quasi-magical and almost sentient. I think it is time for a more nuanced conversation on this. As a sociologist, I often argue for looking at AI from the position of the social. But today we are flipping the script and we're looking at the social through the mathematical. And it is my absolute honor and pleasure to welcome today's panelists, all of whom routinely look under the hood of math. Aubrey Clayton, Theodore Porter, and Anna Steingart. Now, beginning today will be Anna Steingart, who is an assistant professor in the Department of History at Columbia University. Professor Steingart researches the interplay between American politics and mathematical rationalities. Her current project, Accountable Democracy, examines how mathematical thought and computing technologies have impacted electoral politics in the United States in the 20th century. It follows on her first book, Axiomatics, Mathematical Thought and High Modernism, which came out last year. Professor Steingart's work has appeared in Social Studies of Science, Grey Room, and the LA Review of Books, and her work is also supported by the National Science Foundation. Welcome, Alma. Then, following Alma will be Theodore Porter, who is a distinguished professor emeritus of history at UCLA. He has authored many books, including The Rise of Statistical Thinking, Trust in Numbers, The Pursuit of Objectivity in Science and Public Life, and more. His most recent books is Genetics in the Madhouse, The Unknown History of Human Heredity. He graduated from Stanford with an AB in history and earned a PhD from Princeton. In 2008, he was elected to the American Academy of Arts and Sciences, and in 2023, he received the George Sarton Medal for Lifetime Achievement from the History of Science Society. Welcome, Theodore. It's an honor to have you. And closing us off will be Aubrey Clayton. He is a mathematician who teaches courses in the philosophy of probability and statistics at the Harvard Extension School. He has also written a book. He is the author of Bernoulli's Fallacy, Statistical Illogic, and the Crisis of Modern Science, which came out in 2021. He holds a PhD from the University of California at Berkeley, and his writing has appeared in many places, including the New York Times, Nautilus, and the Boston Globe. Welcome to all of us. A little housekeeping for everyone. It is terrific to have our audience. We want you to participate. Please do so by putting your questions into the little Q&A box that you see at the bottom of your Zoom screen. I will be folding your conversations and comments into the conversations after we heard the provocations from our audience, from our panelists today. And with that, I'm going to shut up and I'm going to pass it on to Alma. Thank you all for being here. It is an honor and a pleasure. You're still muted, Alma.
Yeah, just a second. I just need one more thing before. All right, here we go. So thank you, Mona, for this wonderful introduction. Thank you for the invitation. I should say it's really it's wonderful to take part in this, what I think is very important series. And I'm really very much looking forward to be in conversation with Ted and Aubrey. I'm looking forward to this. So in my short talk today, I want to take us back to the 1960s and to focus in particular on okay. Sorry, I just want to make sure that I can somehow get to what I want to do. I might have to do it this way. To take us back to the 1960s, to focus in particular on a set of redistricting legislation that took place after the Supreme Court established what we today refer to as the one person, one vote mandate, namely the requirement that districts should have the same equal population size. Up until that moment, I should say, states had districts of varying sizes, sometimes 2-3 times the size of one of another. So what happened in response to the court's ruling is that legislators across the country had to really quickly redraw districting maps. But not all of them were willing to give up the political power so easily. So what happened in the South in particular is that legislators turned to multi-member districts as a way to curtail specifically the power of Black voters. And what I want to focus on today is the constitutionality of these devices. Now, I think that by this point, some of you might ask yourself, what does this have to do with math, which is supposedly what we're here to talk about today? And what does this have to do with AI, even more, which is the topic of the theorist today? So the story that I'm telling you today is part of my current book project, which examines the growing influence of statisticians, mathematicians, computer scientists on electoral politics in the United States during the 20th century. What I'm interested in the project is how Americans' most basic definition of what counts as fairness and what counts, I should say, as bias have become increasingly construed in mathematical and computational terms. So the book is in no way a history of AI, but I do believe that it does have something to offer contemporary conversation about AI, and in particular AI and fairness. Very often, I think, concern over algorithmic fairness, if it is in housing, if it's in insurance, education, healthcare, are very often attributed to the complexity of modern algorithms. So modern algorithms are based on, right, we know that they're based on massive amounts of data. They require substantial computer power and memory, and they involve, for the most part, convoluted statistical analysis. All these factors, not surprisingly, makes any discussion of fairness seems intractable. And I mean intractable not just to the public, but sometimes even intractable to experts themselves. However, as will soon become clear, questions of how fairness is defined and by whom exist in any attempt to reduce a social or political problem to a set of kind of clear rule-based procedures. And in the case of multi-member district, which I want to kind of highlight this example today, what I'll give you is, what I'll try to show you that how the same example leads to three different definitions of how fairness should be construed. So one simple example and three different definitions. So let me start. So in 1962, Georgia passed the Senatorial Reapportionment Act. What the Reapportionment Act did, it divided the state to 54 seats approximately of equal population. However, the state did not want to give up, according to the state, I should say, did not want to give up on its county system. That meant that even though there are seven kind of most populous counties, even though they, in principle, they were divided into districts, and that the representative of each district had to live in that district, when it came to voting in these populous countries, representatives were elected on a county-wide votes. So what it meant is that a voter in Fulton County, for example, which is the state's most populous county at the time, voted for 7 senators, while a voter, for example, in one of the smaller counties or one of the smaller districts voted for only 1 senator. So if you're a voter in Fulton County, when you come to vote, you vote for all 7 senators for the 7th district of Fulton County. And this was a way, I should say, to decrease the power of Black voters in particular by diluting the vote. So Water, in one of Georgia's populous counties, then ended up challenging the plan. What they argued is that the populous counties had their votes diluted and that they should have their votes counted only on a district-wide basis. And they came up with a way of an argument, a way of the way of kind of to put their claim. And to do that, what they put forward is what they conceived of a very simple mathematical argument. They noted that the population of District 34, which was one of the 7 districts of Fulton County, had about 80,000 residents. They said to the justices, assume, for example, that all the people in the district mobilized around exactly the same candidate, and assume that they voted for that specific, to him or for her. They said one can still conceive of a scenario in which said candidate would not be elected. In fact, what they claimed is that only 18% of the population of Fulton's other 6 districts would suffice to override the 100% vote of District 34. So what their analysis was based on is this idea that the population of Fulton County, the Fulton County's other 6 districts was about 473,000, and that 85 inhabitants represent approximately 18%. That's where they come up with this idea of 18% of the rest of the 6 districts can 18% can overrun the desire of the 100% of one district. So if the entire population of a single member county, a single member district, I should say, would vote for the same candidate, the candidate would inevitably represent a district, but this was not the same, it would not hold true for a multi-member district. So this is the argument, and the argument was sufficient, I should say, to convince the district court that Georgia's senatorial apportionment represented this invidious discrimination. Now the case got to the Supreme Court, and the Supreme Court disagreed. And this is a quote, "There is simply no mathematical disparity," the court majority announced. Since any Fulton County voters was able to vote for 7 as opposed to only 1 senator, there was not, the court reasoned, any discrepancy between the weight of his or her vote and that of a resident in a single member constituency. In other words, since a voter in Fulton County was able to vote for 7 representatives when the voter, when she came to the voting booth, she was voting for 7 representatives, the court reasoned that her vote was not diluted. So I just gave you 2 ideas, right? That the vote is not diluted, the vote is diluted. And now let me, if these 2 opinions are not enough, let me represent the difficulty with weighing votes by giving you yet another opinion, according to which the votes of voters in the populous countries were not undervalued, but overvalued. And this analysis was due to John F. Banzoff, who at the time just got his law degree, but before that he was at MIT, where he was familiar with mathematics, had a mathematical education, also computational techniques as well, I should say. Banzoff began by offering a measure of what a citizen's voting power should be understood to be. According to him, the way we should understand the term is to mean the ability of a citizen to affect the election of a representative. What Bansef was after was a way to codify and quantify the definition, or this definition, I should say, of voting power. And it is here that for him, combinatorics really was helpful. He said, let's consider a district with 3 voters, and we are voting on some measure that's basically yes or no. And he says, if you look at it, if we look at this kind of district, there are basically 8 permutations. If you want to figure out what's the voting power of A, we should ask ourselves, when will the final decision change if only A will change her vote? If A will move from yes to no, from no to yes, then the overall decision of whether or not the measurement will pass or not will actually change. And what he does, the calculation says in 50%, 4 out of the 8, 50%, her voting power of every person in this district is 50%. What happens, however, if the number of people in the district grows, right? It means intuitive that it is clear that there are more people in the district, the voting power of each voter then decreases. But by how much? That's a question. And if the district has n voter, the number of possible voting combination is equal to 2 to the n, again, discriminatoric. And for voters to affect the change, until that all the rest of the population divided exactly in half. So half of the population, let's say, voted for one candidate, the other half of the population voted for another candidate. It's my vote will then change if I decide yes or no. So by applying some basic combinatorics tools, Bansef showed that the number of such combination where the rest of the district divide in half between yes and one and a half going one way, another, is this combinatorical, the n factorial. Now, it doesn't really matter if we follow the math. I go through it very fast because we only have a few minutes. But the point of Bansef was actually very simple. His point is represented in this table, which is that what the truth is that the voting power does not decrease as an inverse of the size of the district. So if that was the case, that's the column all the way to the left. If the population is 3 people, then if you believe that it's inverse of the population, it's a 1 over 3, 33%, where in fact it's 50%. And he was able to show that if you do that, that the voting power did not decrease as an inverse. What that meant then, that if you multiply by the number of persons in this district, how many times you can vote, if you multiply 3 by 50, that means that a person in that district is worth 150. The same 9 times 27.4 means that they vote more than 100. In other words, the vote is actually not decreased. Their vote is overvalued. I know I went through also all this very fast, but even if this quickly, if I've done my job right, you will find all 3 positions to be correct, or at least reasonable. The argument by Georgia voters, the one by the Supreme Court, and Bansef analysis, each has its merits. I personally consider each one to offer one measurement by which the weight of voters could be compared to one another. And on the face of it, neither one is more accurate or correct. To make a case for one or the other would require one to engage simultaneously in both political and mathematical reasoning. In other words, there is no way to separate the mathematical and the political, and mathematical soundness does not entail political inevitability. Defining fairness in an AI system is a complex problem with many, many stakeholders. But as the history I just outlined makes clear, the basic question of how to measure fairness predated the algorithmic age we now live in. The history, I hope, will help us resist some of today's hype and remind us that some of our difficulties are not rooted in the latest technological development, but rather, I think, they inhere in the incommensurability between mathematical and social rationale and the wide room for interpretation yawning between the two. Thank you.
Thank you very much, Alma, for this fascinating take, and I'm handing it over to Theodore.
Thank you, and it's a pleasure to be here. I guess you have the idea already that on the one hand, mathematical reasoning and mathematical tools, and since AI has been emphasized here too, we perhaps could say a few words about that, that these are topics that sometimes, in fact, often are trying to regard the mathematical issues of, for example, elections as strictly given by technical rules and technical developments. And as the last talk illustrated, in fact, there's very often, sorry, we have a rival. That on the one hand, there's so that there's so here we are in a public location, which shouldn't have produced phone calls at what's 10 p.m. here. Anyhow, that what we is often like to view as highly technical topics, and certainly have an important technical dimension. Indeed, that technical dimension is important enough that the issues really matter and engage mathematical reasoning and mathematical tools at a high level. At the same time, there are often ambiguities, almost, necessarily as a result of the difficulties of carrying out a thing like this in a census. On the one hand, censuses have been going on for, for 2.5 centuries, and the technologies have become quite sophisticated, and yet somehow there always are ambiguities that would exist even if everyone was was working with goodwill, and often the politics is not performed with goodwill at all. And again, the talk we just heard illustrates that. A kind of a broader issue that I would like to emphasize here, and I'm going to say a little bit about AI, though I know very little about AI in some sense, but it appeared on the scene. Actually, I retired last year with AI was still kind of in background, and suddenly everybody thinks that AI might be undermining our grading systems, for instance, and our educational systems, that AI would replace the reasoning of the learning of the student with products produced by purely computer-based technologies, and those computer-based technologies are very important, but I feel like it's often being discussed in a misleading way, kind of on the supposition that that when you have a tool like artificial intelligence, it emerges from outside our experience as something produced by high technologies and by mathematical methods, so that it has supplanted the old ideals of, for instance, of education, and replaced them with tools produced by that could be done by machines. On the one hand, I think it's important to recognize the ways in which these technical machines are produced in a complex world. That they also that AI is clearly a technology that matters, but it doesn't seem very likely. In the first a flush of excitement, there was a lot of fear that AI was going to replace our educational systems with a kind of technologically aided cheating. Again, it's not that this is totally inconsequential, but in fact, the AI is a set of technologies, and even its name has existed for several decades. It is a technology which has been powerful, in a way, but which is a product of human activity and not something that came in from outside. So, I mean, if we recognize the ways in which, in which these technologies are created within societies rather than by purely technological means, we recognize on the one hand that that these things are never cut off from the societies within which they work. Well, that would make us, in one sense, that would make us maybe perhaps more nervous that that we can't trust them. And indeed, our ability to trust them depends on not only the power of the technologies, but also the worlds in which they're worked. And at the same time, the fear that well, I mean, again, I think in my department of history, there was talk, and I think in many places that perhaps AI should be banished. That any use of AI would be a ground for failing your courses, or perhaps even being sent out from your schools. And that supposed, I think, that a relationship between the technologies and the and the behavior of the students, which is misleading. Again, the technology has been going on for a long time, and it in fact, yeah, I mean, another way of thinking of it is that the technology actually can be used, in conjunction with tools. And seriously, if you are anxious about, or you're paying attention, there is no way that a technology like AI can be banished from schools. On the contrary, it's I think that pretty soon people were recognizing correctly that AI would be incorporated with other technologies, and the fear of cheating remains a real one, but it's not perhaps different from, except in maybe degree of sophistication, it's not so different from what was there all along. So my general conclusion, which is certainly valid for these complex interactions of statistics and, for instance, voting, also is important, for questions of what counts as a student's own production and what's going to be legitimate. What legitimate aids can be brought to bear in schools. And I have to say, many other things which I and others could talk about, that in fact the technologies of mathematics and others are not in general produced from outside by experts working alone or working only with other experts, but are always allied to other tools and other ambitions and human skills and actions that make I mean, make it important for us, if we're to deal competently with issues like these, to recognize that human and social actions are part of the story all along, and they both can be used to humanize and to make more reasonable, and can be used to to corrupt and to undermine. So if we're to deal with mathematical technologies, effectively, and to get from them what they can possibly do, the best that they can do, we have to recognize this double side, this that what looks extremely technical, very often has a human side. It's not only that humans are affected by mathematics, but that they mix with each other and shape each other and create issues that involve, the technical and the human, the technical and the social at the same time. So that's a very general perspective, which I think is important to, to start out with when we are asking questions about technical tools, computers, and mathematics. So thank you for your time.
Very many thanks, Theodore. Much appreciated. And Aubrey, I'm gonna pass the baton over to you.
Thank you so much. And thank you for the invitation. I just want to use my time today to say a few provocative things about some of my favorite subjects: AI, statistics, and the eugenics movement. And I'll start with what I would consider to be the problem. And this is a problem facing science, but I think also society more generally, which is that science needs causal reasoning to function. Okay, so if you imagine a version of science that did not include causal reasoning, causal statements, it would be reduced to claims like the following: that CO2 levels are associated with global temperatures, that taking a vitamin is associated with improvements to bone density, that reading to children in early childhood is associated with their educational attainment later on. But of course, that's not what we need from science, right? We need statements that capture more than that, including the results of interventions. So when talking about CO2 levels, what we care about is not that they're associated with temperatures, but we care about what would happen if we reduced carbon dioxide levels. And if we're recommending a vitamin or a medication or something, we care about what outcomes a patient can expect if they take that intervention, right? Or if you read to a child, what kind of effect will that have on them later in life? And all of those are causal relationships. And the problem, as I see it, is that statistics, which has become the kind of dominant language of science over the course of the last century or so, just does not have a vocabulary for those kinds of causal relationships. It does not allow you to even talk about causes, right? The only thing that statistics can provide is tools to measure associations in various different circumstances. So, of course, everyone knows the statement that correlation does not imply causation, right? But the question is, if that is true, which is almost a cliche at this point, what does imply causation? How do we identify causes? How do we even define a cause? And these are things that statistics just does not have a language for. And the reason, historically, sort of the story of statistics that led it to be the way that it is largely as a result of the work of one person, and that's Karl Pearson, so shown here, who was a towering figure in the development of statistics in the late 19th and early 20th century, enormously influential person, very, very prolific author. And he had basically a philosophical objection to the idea of cause and effect, stemming from his sort of young life, his earlier days studying philosophy. And he essentially designed statistics to remove the whole notion of cause and effect that had been present in science up to that point. And so he described this as basically an epiphany that was due to Francis Galton, who was his great mentor, that it was Galton who freed him from the prejudice that mathematics could only be applied to natural phenomena under the category of causation. And he called the idea of cause and effect a fetish amidst the inscrutable arcana of modern science. And he was very, very outspoken that, in his view, the mission of science, as he said, is not to explain, but to describe. That is, to discover a descriptive formula which will enable men to predict the nature of future perceptions. And the reason that he did this was really, as he put it, to establish a kind of solidity that theory or causal relationships were basically always subject to some amount of consensus, some amount of exploration, theorizing, consensus building, that they could, things could rise and fall in popularity, and over time, different explanations could kind of come to the fore. But these things like his descriptive formulas, which are things like correlations or measures of association, or the other kinds of formulas that he came up with to fit to the data, as he said, they will last for ages, that basically they are not subject to the whims of society as things come in and out of fashion. And so for him, I think that represented a kind of enduring nature, that anything that he came up with as a descriptive formula, a prediction, a relationship that he found in the data would endure beyond just whatever the kind of historical moment that it was in, which was something that was very desirable for him. Now, why was it so desirable? Well, in large part, Pearson was using these measures of association, these correlations and so on, in the service of his study of human heredity, right? So for Pearson, the main kind of rhetorical maneuver that he engaged in was to look at some data, right? Could be data on traits between parents and children, between siblings, between different family members, or data on the correlation or associations between different sorts of negative or undesirable traits in a person, right? And he would come up with these tables of correlations and this kind of map of associations between pairs of these things. And then he would use that to craft a theory of heritability, that basically all of these things had a basis in heredity. And this is before really the theory of the genome, but if that would become the story later on, that these things are genetically determined, right? And therefore passed on from parent to child. And so for Pearson, that was the scientific basis for his arguments and proposals for the eugenics movement. So in addition to being a towering figure in the world of statistics and science, Pearson was also a leading figure in the eugenics movement of the late 19th century, early 20th century, taking over from Galton. And so that was really his driving motivation, right? So the kinds of record of facts that he described as being enduring, and the kinds of descriptions that were not subject to societal whims, were things like his conclusions about the necessity of these eugenics proposals. So he would say things like, these are quotes from an address in 1907, that the growth of human sympathy has been so rapid during the century that it has cried halt to almost every form of racial purification. And then later, sort of expanding on that idea, he said, education for the criminal, fresh air for the tuberculous, rest and food for the neurotic will not save the offspring from the need of like treatment, nor from the danger of collapse when the time of strain comes. They cannot make a nation sound in mind and body. They merely screen degeneracy behind a throng of arrested degenerates. So these were arguments for the futility of various kinds of social programs that were becoming popular at that time to improve living conditions, because, as he said, these societal ills that we're concerned with are determined by heredity, so they'll just recur in the next generation over and over again, unless we do things like his eugenics proposals for sterilization or what have you, selective breeding. And while I think it's very fortunate that movement has largely died out and lost popularity, although come back to that in just a minute, I think that Pearson's way of thinking about science and about statistics, and particularly the idea that the mission of science is to describe rather than to explain, would feel very much at home in the contemporary work of data science, and in particular in the world of AI. right? So when we think about what AIs do, what they're kind of built on, kind of structurally, mathematically, all they are really capable of is finding in the data associations, right, in whatever form is applicable for that problem, right? So they are essentially just more complicated, sophisticated forms of Pearson's descriptive formula, right, that measure the association between tokens in a sentence or pixel values in an image, with that image being of a particular object or whatever is relevant. But those algorithms, those engines, do not have embedded in them a causal framework, right? They do not understand causes. They don't reason causally. And so that's how you can end up with, for example, in the screenshot shown here, conversation with ChatGPT, where if you ask it a sort of variant of a classic logic problem, where you say, let's say a farmer with a wolf, a sheep, and a grain needs to cross a river, and he has a boat that can carry them all, how many steps will it take for the farmer to cross the river? ChatGPT cannot reason causally about that situation. Instead, it goes back into its corpus of text data and finds that questions of this sort are associated with answers of the following kind, that to solve this classic river crossing puzzle, we follow these steps where the farmer has to go back and forth across the river with the sheep and the wolf and the grain, etc. When actually in this setup, the farmer could just carry everything in one trip across the river. But the engine does not know that. It does not have the logical cause and effect relationship of these animals and the river and the capacity of the boat and the farmer's desires, etc. So basically, AIs cannot think like people because they don't ask the questions that humans ask when they're 2 and 3 years old, which is why at every turn. And I think that that's very harmonious with particularly Karl Pearson's philosophical approach to the mission of science, right? Not embedding assumptions or stories about causal relationships, but rather just letting the data exist kind of on its own and extracting from it measures of association or descriptive formulas. And so the last thing that I want to say is that the reason why causal relationships are important, I think, is first of all because ultimately what we want are causal statements. And I think if we are not explicit about the assumptions and the kind of storytelling that's necessary to describe the world causally, what will happen is that will create a vacuum which will be filled by implicit biases, right? And this is really what's going on in the work of Pearson himself, right? If you think about his work on human heredity, it was never the case that he actually adhered to this mission statement that he should describe but not explain. Of course, he had explanations in mind for all of the different kinds of things that he was talking about, these hereditary, social ills. His explanatory theory was that they were passed on from parent to child, right? And that they therefore would be resistant to interventions at the social level. But those are explanations. Those are causal assumptions, right? That's claiming to know the result of an intervention, what will happen if you do something. And just to give you a couple more sort of recent examples of that, on the left here, this is a poster from a series of ads in the New York City subway about 10 or 12 years ago, where there was a campaign to combat teenage pregnancy in the city. And it had these messages such as, I'm twice as likely, this is from the perspective of this sad toddler, I'm twice as likely not to graduate high school because you had me as a teen. And as a kind of explanatory footnote, it says kids of teen moms are twice as likely not to graduate than kids whose moms were over age 22. Right? So the statement in the footnote is a statistical statement of the kind that we can validate with correlation measures or tests between two populations or whatever statistical measure of association we want. But the statement in the ad is a causal statement. Right? It's what will happen because this person had a child when they were a teenager, right? That they reduced the likelihood of the child graduating from high school. Okay, similarly, sort of what's on the right is a picture from some coverage of a startup company from a few years ago that claimed to use AI sort of computer vision to detect insurance fraud. This is a company called Lemonade. And basically that went about as badly as you might think, that, as it says in this article in Vice, that the insurance company claimed it can detect fraud by looking at nonverbal cues in videos of people. And it removed its claim after some harsh criticism and raised questions about not just the dystopian aims of the company, but also about the actual capabilities of its AI and what this AI is used for. And so I think these are relevant examples of the kinds of causal stories that will fill the void implicitly, right? In the absence of an explicit kind of causal framework and a statement of assumptions of what the actual causal relationship is between these variables in your data. And so I think as people who practice in AI, we should be cautious about this, because what this tells me is that without a kind of careful consideration, just looking at the data and extracting measures of association, we will end up reinventing things like the eugenics movement or phrenology, right? And that it will seem to come about from the data naturally and from the algorithms, kind of without any help from the scientists, when in fact what that really represents is our kind of implicit bias, insidiously making its way into our conclusions. All right, that's it for me. Thanks very much.
Thank you so much, Alma, Ted, and Aubrey, for your really amazing contributions. Alma, we heard from you about the long history of thinking mathematically about bias and fairness and expressing political power in mathematics that deeply impact how we distribute power or withhold power from communities. And Ted, you've reminded us that there are ambiguities that remain in the mathematical tools that we've sort of packaged into these very sophisticated technologies that we use in our everyday life, and sort of eloquently pointed us to a conundrum that we find ourselves in education at the moment, as we're faced with that, and reminded us of the fact that trust doesn't just depend on the tech, but also depends on the social world in which this technology gets embedded. And then Aubrey, thank you so much for your work on statistic and eugenics in this conversation, and also some other pieces that you've published. And you basically showed us that there is this sort of social commitment to causality that we elevate above the quote unquote true nature of the mathematical operations that are in place, which are descriptions of relationships, which of course has then again everything to do with power if we think about how this affects ideological and deeper problematic and awful movements like eugenics. And so I'm going to pause here and remind the audience that this is the time now to put questions in the Q&A box while I have the privilege of asking my questions first. And I'm very excited about, because I've been sitting with those for a long time as I've read all of your work in my research. And my first question for you is about language. All three of you have spoken about the relationship between mathematics and language, spoken about how expressions of mathematical assumptions that really are social assumptions impact our social world. And so you've all expressed how this language sort of unfolds in different ways. You've also all alluded to math being a language that maybe not everybody speaks, or not everybody has the same access to, and yet that is quite powerful. And so my question to all of you is there a place for talking about the language of mathematics as we unpack the social impact of artificial intelligence systems and other deeply impactful mathematical technologies in our everyday life? And this is a question for all of you, if you could take turns responding to that, and maybe we'll go with Alma first.
Sure. Thank you for this, Mona. I think this question of language is an interesting. It's very. I mean, the question of language is a really interesting one. And I think it can kind of this idea that it comes up in all the conversation. I think that part of what I was trying to get to, and part of what I think is sometimes gets missed, is that once something just get codified, and this can be, and I'm trying in kind of mathematical way, and that can happen. Part of what I wanted to show is that doesn't necessarily relate necessarily to computing. That happened before, or it doesn't necessarily have to do with computing. But once something starts to get some idea or some concept that we might have, for us, a concept, fairness or political fairness, that's my example that I have. What is one equal, what, something like something that we all used to use. We all use all the time, one person, one vote. But when if we talked about it and I told you one person, one vote, we always have some understanding. We all think we're talking about the same thing. But when you try to implement it and realize, and if you're trying to think about, okay, so what does that mean in this context, and you're trying to kind of come up with a way to measure that, it's actually not simple at all, right? There's some kind of clash between the kind of rule-based reduction of something that seems to be like a very kind of intuitive and basic idea that we have. So I take that to be kind of an important thing to point to. This question of intelligibility and who has access, I think that's kind of what and I think that's kind of part of what you're trying to get to, this question that map the language should not everyone speak. I think that this is where there's all this literature on accountability and AI. And the accountability can mean different things. And I think that part of the way I like to think about it is in some way that we should come up with different ways to explaining this algorithm, right? There's a way of describing the algorithm in a very kind of very technical language. There's a way of explaining what an algorithm does and kind of what's the social implication of algorithm. There are different registers that we can actually think about when we think about how to describe this algorithm. So we can privilege mathematics, but mathematics is in no way the only way that the only language that we have to try and think through this algorithm that today impact all our life. And I think, yes, some people have access to different understanding of how the algorithm works, but we should always operate under the assumption that we should think about this in different I think about it as kind of different registers.
Ted, the language of math. What are your thoughts?
Yeah, thanks for this. The language and math are both extremely, all embracing, ways of thinking and doing. And I'm not sure what to say in general, except that, one, notion of this relationship, tries to bring mathematical and and let's say verbal language together, and that is important, but can easily leave out aspects that are fundamentally important for users and for those who are engaging in mathematical reasoning as a professional activity, that somehow it's important to be intelligible as much as possible to larger audiences without denying the special skills that trained mathematicians have. So I think it's easy to go wrong and to try to either to cut off the relationship between these things, or at the other extreme to say that there's it's all just language. So in fact, a lot of sophisticated reasoning takes place within language of with whose significance is verbal, and some of what you've heard here reflects that. But at the same time, this kind of reasoning can be quite different in different contexts, and involving people with different levels of skill and commitment.
Thank you, Ted. Aubrey, as a mathematician, the language of math.
Yeah, it's a very it's a very pertinent question. I think what struck me the most in Alma's remarks, as you said also, is that you can take a word like fairness, and then when you try to apply it in the real world and actually pin it down to a mathematical definition, you might end up with sort of competing versions of that and competing conclusions. And I think that just speaks to maybe some of the ambiguities of natural language as contrasted with math. But then when we're talking about statistics or AI, we're often sort of colliding those two together. So one thing that I've often remarked on is that in the world of statistics, many of the tools that we use have these kind of names that are like advertising for that technique. And so they're not just value neutral descriptions of what it does. They are kind of normative descriptions of what you should do. So there are words like unbiased or admissible or robust or what have you, because of the history of how those tools were developed and the social problems that they were being applied to and the kind of controversies that were at play that they were being defended against. And I think that, that also just reminds me that these things don't exist in a vacuum, that they are always applied in the context of, some very high stakes argumentation in society, and that we have to be conscious of that. And I think even the name artificial intelligence is a product of branding and advertisement. In many cases, it's not entirely clear what that means. And some of these things probably, if you didn't call them artificial intelligence, they might not seem so impressive or sophisticated. But that's part of the brand and part of the conversation and the discourse that we're having now. So I don't know.
Thank you all for that. I want to dig a little deeper here. And I do this with my sociology hat on and sort of a concern for essentially predictive technologies becoming infrastructural for social life. And what I'm trying to get at here is there seems to be, at least from where I'm standing, a particular and very strong commitment to prediction as something that ought to organize society. Aubrey, you spoke about this a little bit in relation to sort of causality versus correlation, in Alma and Ted, and was in your contributions as well. So how do we begin to unpack that questioning if that happens and how that happens? Because if we look at these technologies as integrated into social life, they embed a certain commitment to the future, a certain notion of temporality or time, right? And so that can preclude certain ideas from developing or privilege others. So my question for all of you is, and maybe Aubrey, we'll start with you. What is the, do you see there being a social problem? And I will note, I find it extremely interesting that we're talking about the social, even more than the mathematical in this event, with prediction being embedded into our socio-technical infrastructure in the way it is through artificial intelligence technologies right now. Maybe we'll go Aubrey, Theodore, and Alma. Prediction. Is there a problem with prediction? And if so, how do we get at that problem? And then we'll take to audience questions.
So yes, the short answer is yes. And I'm reminded of the aphorism that the prediction is difficult, especially when it's about the future. I think that it's a technical problem, but it's more importantly a social problem. And as I was hinting at in my remarks, I think one of the things that emerges from this kind of causality neutral or value neutral approach to extracting predictive information from data, particularly historical data, is that there's an assumption that basically whatever mechanisms were at play in production of that data will persist, right? So that basically the future will be like the past in every way. And so we're just predicting things within the kind of confines of the same process that generated the data originally. And I think that's a fundamentally kind of nihilistic view about the progress of society, right? So if you're doing some predictions on, race and demographics and credit quality or whatever kind of outcome you're measuring, you have to acknowledge that the data that produced that will have embedded in it certain biases, right, that you hope will become less over time, or that we're working hard to eliminate over time, right? And so if you just use the algorithm as a kind of black box and say, give me the prediction based on this individual's characteristics, it will just reproduce whatever those biases were, and it won't allow you to kind of move forward. So I think that prediction is certainly very important. Obviously, it's going to be a part of every facet of society in the future, and we're going to be using these tools to assist us with the prediction. But I think we have to be more explicit about what are the kind of assumptions and the dynamics that were present in the data that was trained on, so that we don't accidentally end up reinventing redlining and phrenology and the eugenics movement, and basically just enshrining those biases as fact going forward.
Thank you, Aubrey. Head, prediction.
No, I mean, I think that Aubrey's point is the one I would also want to emphasize, that on the one hand, prediction is, well, how can we do without it? I mean, so it's difficult, especially when it concerns the future. And of course, it's always about the future, and we can't do without predictions. And yet, typically, they involve uncertainties, and more than and sometimes almost systematic, or they incorporate biases that we didn't need to have there. And when it's a subtle business, and yet it's not beyond our capacity to recognize these mismatches and misleading aspects of assumption. And we can do it better, but we never do it perfectly. We have to be modest, but we have to be bold.
I mean, I think the one thing I would just want to add, and I think I take it to your point of asking kind of, is there a problem with prediction? So I take the point, right, that, and of course, prediction is necessary to some degree in certain domain of policy, let's say. But I kind of what I'm trying to understand what I think you're getting to, which is in the way that this technologies of prediction are actually ended up creating the future. They're not just predicting, but actually end up kind of closing certain avenues, creating certain kind of futures. I often think back to the work of Donald McKenzie, and he has this book on financial markets, which the title of the book is "An Engine, Not a Camera," which I like that, because basically that's the argument. The argument of the book is in the title, right? Which is this idea of all these economic models that were supposed to be a camera to how the economy works, actually ended up being an engine, meaning they ended up dictating how the economy ended up working, right? So the problem, I take part of the problem that you are trying to get to, which is there a problem with these prediction models that are going to actually become engines in some way of the kind of and restricting the society that we have. I do have a question for Aubrey. Am I allowed to ask a question myself? Yeah,
Go
okay?
for it. Yes,
Oh,
absolutely.
right. So Aubrey, I do have a question for you, which is, I think I take your point, the kind of distinction that you make between the kind of causality model, the science's causality model on the one hand, and the kind of correlation model that we have in AI. But and I think it's important, and in your work, you obviously show that. But I want to know I feel like to a certain degree you're too quick to give up on correlation and statistics. There's a way of reading. I don't think you are doing it, but I think there's a way of reading what you're saying, that you're too quick to just throw statistic away completely. So I'm thinking about the examples that you have, right, about let's say vitamin B and bone density, but it made me think more broadly about a lot of the ideas about if a certain drug is actually safe or not safe, right? There's those experiments are their statistics that goes into this, right? At the end of the day, statistics play a really important role. I mean, Chris Phillips is working on a book right now. Chris Phillips is working on a book about biostatistics, which is all about how the statistical knowledge became extremely important to defining, right, what we consider to be safe and what is risky and what is not safe. And so in some way, I don't think you're saying that, but I kind of wanted to kind of push back. I don't think you're saying that we should give up on statistics and correlation when we're thinking about experimental, experiments for kind of medical and kind of the medical domain, or we can come up with many other examples where statistics obviously play an important and crucial role. It is probabilistic, right? At the end of the day, there is a kind of probabilistic argument there of whether or not the drug is safe or not. So I was really curious to how far do you want to, I guess I want to hear how far do you want to go with this kind of argument?
Yeah, so I totally take the point. I think this is probably a much longer conversation than I'm prepared for today, but I think that you're right that there is a role for statistical measures in maybe identifying certain associations or extracting key relationships in the data that could inform some experiments. So, I think back to one of the big uses of statistics in the last century was to identify the correlation between smoking and lung cancer. And obviously that's not a situation where you can do a randomized controlled trial, but you can make arguments from the data that association is real, and that was the basis for some really significant improvements. At the same time, you can also look at that data another way, and people like Ronald Fisher certainly looked at it to say that correlation did not prove a causal relationship, and that it could be that there's something underlying both smoking and lung cancer that causes a person to have both. And so I guess the only thing I would say in brief is that I think that these are complementary to each other, but that there's always going to be a necessity for a causal framework to make sense of the associations that you find in the data. So, for example, if you think that story is possible, that that there's an inflammatory condition generally that causes both someone to smoke and have lung cancer, that's going to lead you to different conclusions from the data, even with all the same associations, all the same correlations being in place. And so, there is a vocabulary for this that exists largely outside of the world of statistics, and things like confounding variables and collider bias and directed acyclic graphs and sort of causal diagrams that allow you to basically just encode those assumptions and then guide you in how you are going to treat the data and reach conclusions. But I think that they're sort of complementary to each other, but I think you can't have science without causality is the main point that I would want to take away.
Thank you both for that. I'm going to take this as a cue to start bringing in our audience questions. And I'm going to start with a question from Emmanuel Moss, who is basically, I'm not going to read the whole question, but I think what he's trying to get at, and Ted, this is a question for you, I think. He's saying, well, in the world of statistics, folks have been trying to do causality in many different ways. Are any of those ways particularly compelling? And I'm going to ask, are they compelling to you? You wrote a lot about statistics.
I mean, well, on the one hand, though, I perhaps often trying to bring out the ambiguities that are typically present in dealing with hard questions like this one, that there certainly are things that statistics can do, and that the general scheme of separating using comparable groups, to the extent possible, but through tools of randomization. Though these things have been abused often enough, yet when and sometimes you can't do it, and yet it is it's as an ideal of statistical reasoning of reasoning. It seems like it has its validity, which remains intact, and yet you almost never can randomize completely. And one has, I mean, certainly the story of cigarette smoking and tobacco, for instance, is one of amazing bad faith, as well as, somewhat difficult, but yet, situations that remain, at the end of the day, that is knowledge that remains totally convincing. So, you never, you have no, complete, magic tools, and yet, this kind of the tools that are sometimes can be made available, and the basic techniques used to analyze them are can be quite convincing, the best we can know, and we have to recognize sometimes that we do know a lot too.
Thank you, Ted, for that. And of course, sort of the disciplines speak to that as well, right? And for example, the growth of data science as a discipline speaks to that as well. I have a question for Aubrey, and then another one for Alma. This is from Dawn Nefas, Aubrey, who's stating that her understanding of AI, quote, air quotes, is that there are meant to be priors stemming from Bayes, which to her mind sounds a lot like notions of causality. How does that figure in your work? Is part of what you are saying that that is sort of all to do with sort of social underpinnings? Like, can you be a little bit more explicit about that, Aubrey? Maybe briefly, so that we can get 2 more questions in. Yeah.
So I think that's a great question, and the short answer is no. I think those are different things, although they are both important. That you're right that in the world of data science and machine learning, largely has embraced Bayesian statistics as a tool, which is a kind of rejection of part of the statistical orthodoxy of people like Carl Pearson, whom I spoke of. And that is a way of bringing prior information, background information, and assumptions to the analysis. But I think it's different from what I'm talking about, which is assumptions about the causal relationships between variables. And the way that I would just summarize that difference is that to talk about causality, we have to talk about what would have happened if the world had been otherwise, right? If something had been different from it when it was, if we did X, or if a variable was changed from X to Y, then what would have the result have been? And that is just fundamentally something that requires you to go outside of the data, right, to tell stories about counterfactual relationships of what would have happened. And then in order to do that, you have to be willing to use your imagination, your storytelling ability as a human being, to go beyond just what you've observed. And I think that's something that that no statistical tools, including Bayesian ones, are ever really capable of doing.
Thank you for that, Aubrey. I have a question for you, Alma, and this is a provocative one. Andre Sobral is asking, could we consider artificial intelligence as an authority argument in the form of a tool constructed by an emerging elite to assert social control? And you're getting that because you spoke about authority and power quite explicitly.
Yeah, that's a good question. Is that, I guess, is this a question? I mean, I guess there's a few ways to kind of read this question. And I wonder if is this kind of description of this is how AI has emerged. Again, if we're talking about AI today, if it is of social control, then we have to ask ourselves, right, who are the people behind AI, right? I mean, AI doesn't operate, right? There are people putting the money to invest, the people to making sure that there's money in order to operate the kind of data centers that kind of we have to figure out what do we mean, right? Who's behind those tools in some ways, which will, I think, will be an important way for us to try and answer that. And that will remind us that there are always people behind there. Aware of social control. But I don't know if I would be so quick to give up on the idea that, how would I say that, these are just tools of social control. That in that sense, we're kind of giving up our ability to try and like change those tools, right? I mean, I think that it will we'll wait to see what happens. But we can imagine a world in which there's much more regulation on AI, right? And hence there's some kind of regulation that restricts when and where AI. And there's so many scholars that have written so much. I mean, I've written much more eloquently than I ever about these questions about, right, what is accountability and where do we want AI, who does not want AI, right? I guess that I think that we should be wary of giving up so easily some way, so quickly. At least I want to resist that.
And I really appreciate that. Let's not give up on it all just so quickly. And we are at time, and I want to close this out by answering a question that Katrina Yanko posted, and they're asking, where can non-math people learn more about the relationship between math and statistics and policy? And maybe a 2-second answer from each of you. Aubrey, your book and?
My book, Bernoulli's Fallacy, and yeah, I think there's a writing project now called The Legacies of Eugenics, and related authors who have written in that series, I think are a great starting point, but I don't have another go-to reference.
Thank you, Aubrey. Ted, where can folks, non-math folks, learn about math and politics? Also, your many books, and where else?
I'll just, I could give many answers, but I'll just mention something that's quite far from my usual activity, which is a historian, Stephen Stigler, a statistician, who I only eventually kind of understood that he was really defending the subtle means that statistics provides, as opposed to the form of appreciation that has often been presupposed over the years, that you have a formula and or whatever, a technique, and you apply it and you get the answer. Being it's not in fact done well. It's very sophisticated and demanding, and it's worth remembering that. But it's possible. Yeah.
Thank you for that. And on the axiomatics.
I was actually going to say, obviously, Ted Porter's work. I'm sorry, but that's where you need to start. I know before we got in here, I said that I teach it all the time, because I think that's where yes, you kind of have to start there. We'll throw in, besides that, a couple of just works that came out in the last few years. There's Dan Bout's work, fantastic work on the census. There is Matt Jones and Chris Wiggins' book that just came out in the last year about how I'm sure they already all came to talk at this at some point about how data happen. If you're really only interested about voting and questions of voting, there's a book that just came out by a mathematician called Ismar Volek, Making Democracy Count, which just talks about the mathematical voting. So there's actually quite a lot, and even a lot of recent work as well.
Thank you very, very much. And with that, I am going to express my deep gratitude to Aubrey Clayton, Theodore Porter, and Elma Steingart for joining us today for a conversation about artificial intelligence and math, the big elephant in the room. I have truly been waiting for a long, long time to have this conversation. I'm honored that you all joined us. A big thanks to our engaged audience for coming along, asking questions. I thank you all. We are going to be back with more co-opting AI sessions this semester. We will have a conversation about artificial intelligence and architecture next month, and then we will have one on AI and anatomy in November. So stay tuned with all things. This conversation will go up on our YouTube channels. Stay connected. Thank you all so much, and have a wonderful rest of your day. Thank you, Alma, Ted, and Aubrey. It's been a real pleasure. Thank you.
Thank you.
Thank you.